Okay, so pre means that you are visiting your parent first, then your left child, then your right child. Post order means that you're visiting your left child, then your right child, then your parent. And then in order is left child, then right child, and then the parent. And then DFS is, remember, we care about depth, right? So if we have this tree, then we would want to have the traversal look down this way. Whereas for a breadth first search, we care about the breadth. So we care about finishing each layer before we move on to the next. Okay? That's a little quick summary of traversals right there. Okay, so let's practice on this tree. So the pre-order, okay, is going to be, first we need to visit the parent of this entire tree, right? Remember we apply these traversals recursively. So first we're applying it on the entire tree, and so we need to visit 10 first. Then we go to its left child, which is really just this subtree, right? We apply the pre-order on this entire subtree, which means that we visit its parent first, which is 3, then its left child, 1, then 7. And I'm just going to put commas to separate these. Okay, and now we're finished with the entire left child, so now we go to the right child of the original parent. And remember that we again apply the pre-order on each of these subtrees, right? So for this one, we can visit 12, okay? It doesn't have a left child, so we can just go to the right child, which is this subtree. Again, apply it, and so we need to visit 13 first, then go to its left child, see that it doesn't have a left child, so go to its right child, and end at 15. For post, it's kind of the opposite. So we start off from the very left child, right? So as far to the left as possible. And so that means that we need to go all the way down to this one, okay? And so now we're basically looking at this little subtree. So we need to now go to, and we need to visit the 7, right, which is the right child. So 7. Then we need to visit their parent, which is 3. Okay. And now we need to look at the right children, right? So basically we first started the post traversal from 10, right? So we went to its left child, applied it recursively here, and now we're going here and applying it recursively on the right subtree. So in this case, we don't have any left child, and so we need to just start from the right. And so we're going to go from 15, go up to its parent, which is 13, go up to its parent, which is 12, and then finally go up to their parent, which is the root. Okay, and then finally in order, so this is just really going in left to right order, so 1, 3, 7, 10, and then 12, 13, 15. So this is actually really my favorite traversal because you get to write the notes in increasing order. Okay, and then for DFS, it's really just starting at the root and going all the way down until you can't go any further, and then moving from left to right. So we start at 10, we go all the way down to 3, then 1. Okay, now we're stuck here because it's a leaf, so now we backtrack up to 3. Okay, we have another route that we can go here, which is 7. Again, we're stuck, so now go back to 10, then traverse all of this, which is 12, 13, and 15. And then finally, BFS. So this is, again, a favorite because really you just have to read off the notes in level order. So even though they're not connected, right? If you look at 1, 7, and 13, they're not connected, it doesn't really matter as long as they're in the same level. And by level, how do you tell whether they're in the same level? Level refers to how far they are from the root, right? So this is, I guess, two nodes away from the root. This is also 2 nodes away from the root. And so by that definition, they're on the same level. And so you list them right after one another. And again, both DFS and BFS go from left to right. Okay. All right, so that is it. Now let's look at, is this a BST? So this is a kind of tricky question. So if you look at this code, there is a bug in it. It's probably not apparent when you first look at it, but it's based on the fact that you don't really check whether every node, every left child is less than the root, and whether every right child is greater than the root. And so really what you're doing by this check, by immediately returning false, is only checking whether the immediate left child just has a value that is less than t.val, right? So in that case, you would not return false. And again, here you're just directly checking whether the right child only, not the right subtree, is greater than the parent value. And so really it's bad because you should be checking that all left nodes are greater than parent. I guess you could also say root. And all right nodes should be greater than the parent / root. So how do we fix this? Well, this is kind of a rewrite of what we want to do with this. So basically this code is checking if a given binary tree is a BST, right? So if we want to really make sure that it works for BSTs, because if we're just checking whether the direct children are satisfying the invariance, we could just draw up any tree that is not a BST, such as, for example, let's just say, I don't know, I have 10 here and I have 8 here and I have 10 here and I have 2 here, right? And then, or actually this wouldn't work. So I want to actually satisfy the invariant for some level, and then once I get to let's say that this is going to be like 10 and this is going to be like 3, right? So if I have a tree like this one, right, it's gonna actually pass this code. Why? Because I only check locally whether it satisfies the BST invariant, okay? But what I wanna do is make sure that this 10, everything here is actually less than the root, and everything here is actually greater than the root, right? So how do I do that? Well, okay, so I wrote the solution and I want to go over the logic behind it. So you have this helper function precisely because just being passed in a tree node is not enough information to decide whether the tree node is actually a binary search tree or not. And the reason for that is because, again, to determine whether the BST invariants are satisfied globally, you want to make sure that you keep track of some indication of what the range currently is, at whatever subtree you're at, right? And so that can be satisfied by passing in some kind of a min value and some kind of a max value. And in the beginning, you're going to be using the most possible minimum value, which is integer.min value, and the most possible max value, which is integer.max value. And you can also find that by looking at the hint. And the reason why we can pass in integer.min value rather than some other numeric value is because we can always assume that for a binary search tree, our nodes are going to contain integers. And so for our BST helper, the base case is when t is equal to null, right? So if t is equal to null, then we know that we've either reached a binary tree that is a binary tree that is a BST, or we have an empty tree, in which case we're just going to return true. Else, right, if the t.val, so if the current node's value is less than the minimum, in other words, it's outside the range, and similarly for the max, it's greater than the max, then we know that we have violated this invariant, and so we can immediately return false. Otherwise, we have to recurse on both our left and our right subtree and make sure that we pass in the correct ranges, right? So for our left subtree, we want to keep the min the same, but now we want to make sure that our left value is no greater than this current node's value. And for our right subtree, is kind of the opposite. So we want to make sure that they're no less than our current node's value, and their max can be however big as they want. There's no limit on that. So that's kind of the idea of applying the BST invariant to actually check correctly whether a given binary tree is a BST or not. And so now we can go on to the third exercise. And again, I really hope that you've paused the video and actually looked at the question and attempted it on your own. So basically the idea behind this is that you want to print out all the root to leaf paths, okay, as a string. And so for example, if you have this type of tree, then the program will print out 10 to 5, 10 to 1, 10 for -1, right? Okay, so how do we actually do this? Again, I wrote the solution out to kind of walk you through how the logic was, at least for the solution. And again, there could be a lot of different implementations. It's just that this skeleton code was given for you. So similarly, like above, we need to have a helper function because just given this, it's not really enough to actually create all these paths, right? We need to keep track of the progress of appending to our string as we go along our tree, right? So we need to keep track of this information. And so basically what we do is we just call with the most general initialization as possible. So the tree node T is just going to be passed in as T. We have K. K represents the condition for when to print out a root to leaf path. So in this case, we want to make sure that it sums to K equals 13, right? So in that case, 10 to 5 is not going to pass the check. It will only be 10 to 1 and 10 for -1. So this K is going to determine what type of paths are going to be printed. And then again, we're going to keep track of this extra information, which is basically what we want to have this function do in the first place. So what are we going to do first? Well, we know that we already check whether T is null or not in the beginning before we call this sum paths function, right? So we don't really need to check here again if T is equal to null. And actually, you might think that, well, we do need a base case, so why can't we use if T is equal to null as a base case? You kind of see why, right? Because basically, the base case for this problem is when you reach a leaf. Because at the point where you reach a leaf is where you need to decide whether you've passed the condition for K. And if you did, then you need to print out the updated path, right? And so really our base case is when T dot left is null and T dot right is null. In other words, it doesn't have any children. So in that case, you have to make sure that if K is actually equal to 0, at which point you have used up, so the summation of all the nodes on your path have equaled K. And remember that we subtract the T dot val in the beginning. And so it's okay if K is equal to 0. You've already counted for this current node's value. Then you print out this updated path, which is the path that you've taken in plus your own value, right? And then else, right, if it's not a leaf, if you're not at a leaf, then that means that you're not able to print out anything, right? But what you need to do is you need to update this path to reflect the node value that you're currently at, right? So path is going to be concatenated with t.val, which is your current value, plus an extra space. And the space is really just kind of an aesthetics thing. I guess it's also kind of mentioned in the directions that you need to have a space between. But basically, you know that there's going to be some other node after you because you're not the leaf node. And so that's why you need to create this space. And if t.left is not equal to null, in other words, if you have a left child, then you need to explore all of its potential root to leaf paths too. And so you need to call this recursively. And then if t.right is also not equal to null, in other words, if you have a right child, then you also need to go and explore the right child. And again, notice that these are not exclusive. If you have a left child and a right child, then you would be calling two recursive calls. Okay, so that is the code. And then for part B, the worst case running time of this function in terms of n, the number of nodes in the tree. Okay, so if we think about what this spec is really doing is we want to really maximize